before, we can also look at what a celestial sphere is. Here. You see, this is a celestial sphere. What is a celestial sphere? I'm referring to, if you're going to watch the video later, I'm referring to figure 4.3 to explain the celestial sphere. Celestial sphere is nothing but an extension of the earth itself. You see?
In the grid.
Yeah, essentially it's a infinite sphere, so to say. Okay? If you were to imagine this as earth itself, can you make sense of those numbers?
Yeah, it's longitude, latitude.
Yes. Okay. If this were earth itself, those numbers would really be
Coordinates.
the longitude latitudes. Okay. Now if I say where is the 45 degree east latitude, east longitude, and 30 degree north latitude.
What?
45 degree east, 30 degree north. What would that point be?
45 degree east, 30 degree north, that would be like this, just above the sphere.
So this will be that, right? This point.
Yep.
Mm-hmm.
Well, a little bit.
This point, right?
Yeah.
That point is the 45 degree longitude, east longitude.
Yes.
So longitude go from east to west.
Yes.
Although the lines run from north to south, longitude is measured from east to west. Latitude, the lines are measured in north and south. Okay. So the 30 degree north latitude. You see that? Where is the tropic of? What is equator?
That's the center line.
That's a 0 degree latitude.
Yeah.
Okay. What is the 0 degree longitude again? We talked about this. What is that? Where does that 0 degree longitude pass through?
The two poles.
Huh?
The two poles.
All the longitudes pass through two poles. But what does that 0 degree longitude pass through? We talked about this.
The prime meridian.
Yeah, prime meridian.
Prime meridian. Where is that prime meridian?
Dead center. North, east, west.
I don't know where.
It's in England.
Oh,
It's a place called Greenwich. Okay, Greenwich Mean Time or Greenwich Meridian is the prime meridian. So if you draw a line passing through the two poles and Greenwich, England, that is the 0 degree longitude. Make sense? So everything. So that is where your hemisphere gets divided into east and west. Yes.
Why is it from 75 degrees to 90 degrees is labeled 1 hour?
Huh?
Why is it labeled 1 hour between?
Yes. So that is a time difference.
Oh, okay. All right.
That is how we have different time zones. You see? Strictly speaking, there is no digital time difference. Okay, there is no digital time. There is nothing digital. You understand? Everything is
Natural.
continuous. Okay. So that is the approximate time difference. You get it?
Yeah.
Now here, what you're seeing here is not Earth itself. This is an extension of Earth. So you have Earth. If you look at a infinite celestial sphere, you can identify the position and the relative position of any orbiting body at a given time instance with this right ascension, okay, and declination. You see that over there. Right ascension is essentially the. So what is the? Where does the right ascension measure from? In this case, where is the right ascension? Do you see the word right ascension?
Oh, it's.
Right ascension. Now I'll go. Everybody gets the idea of celestial sphere.
Yes.
Okay. Let's look at the right ascension. Okay. You see the right ascension here. This is more clear.
Yes.
Okay? So you have a satellite somewhere, right? Right ascension is the angle going from the
Primary.
not prime meridian. Here,
England.
Equator.
it's not an equator.
Oh, now we're talking about.
The x-axis, the x and the z plane.
Okay.
You see that? This line. So it is measured in this, about this. It's measured in the equatorial plane. Got it? It starts from the x-axis. You guys remember what we talked about the x-axis? It's the line joining the center of Earth and the Aries constellation
Oh, yeah.
on the day of vernal equinox. Okay, that is what that line is. Okay, so that line, this is the right ascension. Okay, and this is the declination.
Okay.
So these two can be used to identify an object in space and how those change. You understand? If you're in an aircraft, you generally use latitude, longitude, where you are. But you can do the same thing with the satellite. You can use right ascension and declination. Okay. Now, what you're going to see is this R. I want you to learn how to convert this R. Here, R is what? R is the position vector. R is written as here. Does this make sense? X I plus Y j plus z k. What is I j k?
X, Y, Z.
Huh?
X, Y, Z.
X, Y, and Z. Okay. Just take a look at this. R, okay. Xi plus Yj plus Zk. It's simply the position of the satellite at time t expressed in the ijk coordinate system. Got it? And the velocity is, you have x dot or Vx, you can write Vxi plus Vyj plus Vzk. Okay. How do you convert this to right ascension and declination? Apply your understanding of cosine sine.
How do you write the vertical?
So think about this R, okay. The projection of R onto the xy plane. This line, the dotted line, is the projection of R onto the xy plane.
Yeah.
Okay. So can I say so if I call that as R xy is R cosine delta. See if you
What is delta?
delta is a declination angle.
As largely
And this is for R.
RXY is this line. Okay,
Yeah.
this is delta.
What do you need a sine component?
No, this is the cosine. So this is the R. This component would be sine.
I mean, yes. Okay. Yeah.
Got it?
Yeah. I was thinking.
So RXY is R cosine delta.
Yes.
Yeah, right.
Okay, so you don't need this. Or simply put, cosine delta is Rxy divided by R.
Would you be mad if somebody asked that question?
Huh?
The difference between R and on this, speaking of these perspectives.
So here it is just the magnitude.
Yeah.
Okay, what is the direction of this? This has both x and y component.
Yeah.
Alright?
Yes.
So now can I say Rx is equal to,
Why doesn't that have a direction? Why? I don't understand. That's what I'm asking. Is why did you take the direction away if you were establishing that?
I'll tell you what the direction is.
Okay.
Just so Rx is Rxy cosine alpha. See if this makes sense.
Rx is.
So this is Rxy, okay?
Uh-huh.
This angle is alpha. This is the cosine component of this. This is the sine component.
Yep.
Got it? So you have Ry is equal to R xy sine alpha. You got it? Now if I just substitute, what is Rxy? It is R cosine delta this is equal to, can I say this is R cosine delta cosine alpha?
Yeah.
I just substituted this Rxy here.
Okay.
Okay, R cosine delta.
Yeah. Yeah. Okay. Yeah.
Got it? This is R cosine delta sine alpha.
Yeah. You just did the same thing.
I just did the same thing. What is the direction of this? Does this make sense?
Yes. Yes.
You get it?
Yeah. Yeah. So because you added the direction at the end, now you put.
Yeah. Now what I'm missing is RZ. Okay, RZ is simply R sine delta.
That's why you have a direction. That doesn't have a direction. Yeah.
Okay, so here what I can do is I J K.
Yeah.
Got it?
Yeah.
Instead of x, y, z, I just put I, J, K. Now you can see the correlation. What is this Rx? Can I say this is x I y j and z k? Okay, so now what I can say is x is what? R cosine delta cosine alpha.
Yeah.
X, I just remove I here, okay? I just remove I. X is this,
Y cosine delta cosine.
Y is R
Cosine.
cosine delta
Sine.
sine alpha, and Z is
Sine.
R sine.
Yeah.
Does that make sense?
Yes.
What I want you to do is convert between X, Y, Z or R, what is this? How do you calculate R?
R is the projection of the angle, so
X divided by cosine delta cosine.
Hmm?
X divided by cosine delta cosine.
oh, I know that.
This makes sense?
Yes, it's the magnitude.
Oh, yeah. it is.
Got it?
Yes.
So given the XY coordinates or given the position vector in the XY in the IJK frame, you should be able to convert that to right ascension and declination.
Okay.
Got it? So what you're going to do is, now can you use these formulas first? What is the limitation of using these formulas?
They don't give direction.
No, if I were to give you this, where will you start with the process of computing right ascension and declination?
Look for an angle.
Which these three are the equations you need, okay?
Yes.
Where will you start? Can you use this equation?
No,
Why not?
because you wouldn't have that. Yes, sir.
So that's what you're given R, you're supposed to calculate alpha and delta.
Yes. Well, no, I start with this vegan.
You'll start with this one, right?
Yeah.
Because?
It's one I know.
One unknown. You see, you start with this because there is only one unknown. Here there are two unknowns. Okay, you start with this. You'll be given Z. You know how to calculate R. You compute delta. Okay. And similarly, once you have delta, you can compute everything. Okay. So I want you to learn how to compute right ascension and declination from this. The formulas are given. If you scroll down again, I'm talking about figure 4.5. Okay. So this is the algorithm. Here is some extra credit work for you. You may need this if you're struggling or if you think you're struggling. Look at this algorithm. Okay? You see this algorithm? You see algorithm 4.1? I want you to implement this algorithm in MATLAB.
Do we have MATLAB?
We have MATLAB.
Where?
Upstairs.
Cool.
Okay.
I will help you implement the algorithm. I will teach you whatever basic MATLAB you need to learn. It will really, again, it is really needed. Just because I told you you cannot be, in these days, you cannot be a strictly aerospace engineer. You have to be a multidisciplinary thinker. Practically everywhere you go, they'll ask you, do you know how to program? Okay, if you say, I don't know, they may actually not consider your case. Okay, so that's the reason I'm trying to get you to do programming. And the other reason you want to learn programming is, see, some of us have difficulty with mathematics. Right? If we are exceptionally good with mathematics, we don't need programming. If you have that sense of mathematics, you don't need programming. But if you don't have that, you can overcome that. You can circumvent that limitation through programming. What you can do is you can learn as well through programming. You don't know what the answer is for many of the questions because you're limited in mathematics. So you do it using programming. Then you come back and check what your method will get you there or not. You understand? Okay. So I want you to consider implementing this if you want some algorithm 4.1. I think this probably is in the old book, but the algorithm number should be the same. Okay, just check. Let me just quickly check here.
A little bit.
Yes, it is the same thing. It's page number 193. And again, you can take help from each other, but don't just blindly copy what your colleague is doing or what your friend is doing.
So 193.
193, yes, page 193. Okay? Now, this is one algorithm. We'll quickly do a problem. Okay, how to do this. So, for example, so R is given. R, what frame is this, guys? What frame are we talking about? I told you what frame it is, or what reference frame. The XYZ. It's called the Earth-centered inertial, ECI frame. Keep that in mind. Okay. It's either called Earth-centered inertial or geocentric inertial frame. Does that make sense?
Yes.
Geocentric means Earth-centered.
Yeah.
Okay. Earth-centered or there's only one Earth-centered inertial frame.
So doesn't it like move? No, Earth moves around.
So what is happening is when it is slowly moving, the acceleration is not that much. The frame itself is not moving.
Yeah,
Earth, it's
right.
not rotating with Earth.
Yeah.
It's stuck there. When Earth is rotating, it's stuck there. But it does move, revolve around sun.
Okay.
You got it?
Okay. So the frame revolves around the sun.
Frame
but it
revolves
doesn't
around,
move.
but it is always
It's
there.
fixed.
It's fixed.
Okay.
That is the Earth-centered inertia.
Okay.
So here you're given R is 5368 I plus is 1784 minus 1784J plus 39369 plus 3691K. Okay. And the units are kilometers. Alright, so at this R is at time t equal to, let's say, t1. Got it? It has to be at a particular time instance, right? Everybody understands this?
Yeah.
Because it is orbiting. This keeps on changing. Right? Now I ask you to calculate the compute. Your question is compute RA and this.
You see it? Yeah, this is.
What is this?
It's that,
Declination.
Declination. What is this?
Right ascension.
Right ascension. Use your right hand, Janet. Yes. So always see, if you use your left hand, you get confused. You have to use, somehow they determine that right hand is. So right ascension is right hand.
yeah, I was just like drawing it.
Right. So when you do the right ascension, it is from the. So this is the x direction, and then you do this. This is that x direction. Okay, and that angle is from that x direction, from right hand sense.
Okay, so this is said this is,
So this is, if you look at it, this is that x direction.
yes,
The right ascension is this angle.
so that's the essentially comes up.
Right. So this is your z.
Yeah.
Okay. So it's from this plane. The angle is from this plane. What is the what is the right ascension? What is this right ascension?
The angle,
So you see, if the satellite is here, what is the right ascension?
0.
0. Okay. So as it moves, the right ascension changes. From that, it's right ascension.
Okay.
So here, if you have to again think about this in the sense of latitude and longitude. Is there just one place on the 0 degree longitude? There are multiple, right?
Yeah.
But the right, there are multiple places which will pass through a 0 degree longitude. So the satellite, when the satellite is always doing this, right? The right ascension is kind of fixed. You see that?
Yeah.
If it is always doing this, what is fixed? If it is always doing this, the right ascension is fixed. You understand what I'm saying?
Yes.
If it is doing this, what is fixed? Declination is fixed. What is the declination in that case?
What do you mean? Yes.
This.
Yes.
What is the declination?
It's
No.
0 degrees.
oh.
If it's an equatorial orbit, is the declination fixed?
Yes.
Yes.
Okay. Oh yeah. Oh okay. I got you.
Got
Yes.
No, got it.
He's saying like
If it's rotating along the right ascension.
it? If the satellite is equatorial orbit,
the definition isn't. Like,
So what would the
it's
right
not.
ascension
It's
be?
just going around.
Huh?
Wait.
What would the right ascension be?
right ascension will be changing.
Oh,
You get it? Right ascension is changing.
Yes.
So why wouldn't so in a situation where it's on either axis, they're both consistently changing?
Yes. So if you look at this thing, this curve, okay, a curve which joins this k and this x.
Right.
If you look at that curve as the orbit, the right ascension is fixed.
Right.
You see that?
Yes.
Read this.
Yes.
So similarly, if this curve is fixed, if this orbit is equatorial orbit, the declination is fixed. You get that?
Yes.
Why is the declination fixed? Think about it.
Because it's not like
What is the z component if this is the orbit?
it's 0.
0. So your r or your zi is
0.
0. So your sine delta is 0. Means delta is 0.
Just have an X.
You have just x and y component.
Yes.
Got it? So similarly your alpha would change as well. Now let's do this. So how do you do this?
First, find magnitude.
First find magnitude, yes. So tell me the r is simply root of
X squared.
right 5368 square plus 1784 square plus 3691. Okay, so this is I have the value of this 6754. 6754 kilometers. Okay. Now you know z is
The distance.
No. Come on.
so you can either use what I gave you on the board, or you can simply do this. Okay. So look at the algorithm there. I'll just. Does this make sense? This is the algorithm. Okay. You can remember this algorithm and use it to. Your L is x divided by r. What is this? What is x here? X component. Right? So it is minus 5368 divided by 6754. Okay, so this is equal to minus 0.79 47. Okay. Similarly, m is equal to y divided by r. Got it? And if you look at that value, it is minus 0.264. And n is z bar, which is 0.5462. Alright?
Right.
Now, what you can do is, if you follow that algorithm again, delta is simply sine inverse n. Okay, so your delta will be .13 degree. Okay. Yes.
Just to try to connect what we did before to what's happening here,
Yes.
they used n with the z component because it's one
Yes.
one unknown, right?
Correct.
Cool.
So here, what you're seeing is what I gave you is just look back in your list. Zi is equal to, it was r
So we are sine.
sine delta I, right?
Yep.
So here, sine delta is equal to z over
R.
r. This z over r is n. Got it? So delta is simply sine inverse. You can correlate. That's one. So you have delta, and then you have. There is a trick. I want you to understand. So you guys. Remember this?
Oh yeah, all sine, tangent, cosine. All are positive, sine is positive, tangent is positive, cosine is positive.
Right.
Yeah.
Okay. So the way we used to remember is all silver teacups.
Also the decouples.
Okay. What that means is here all the angles are positive.
Also the teacup.
Sine of 0 to 90 is positive. Cosine of 0 to 90 is positive. Tangent of 0 to b 90 is positive. Okay. Here only sine is positive. Sine of 90 to 180 or 90 plus to 180 is positive. Cosine is negative. Tangent is negative. You understand?
Yes.
Here only tangent is positive. Sine, cosine are negative. 180 to 270. Here cosine is positive, which means 270 to 360.
What about when you go like three
Huh?
dimensions though? What about when you add a z component?
So angles, 3D geometry is another level. Okay. So we only talk about 2D geometry.
Yeah. Okay.
There are actually 3D-dimensional angles, but that's for another day. But understand this. What that means is, when you take the inverse of this, of sine, or for that matter tangent or anything, you always get only one value. But if you take the inverse of, let's say, if you were to do P equal to cosine inverse Q, okay, what could be the value of P? What I'm saying is, can I say, so this, can I say cosine of P is equal to Q?
Yes.
Very fair.
Correct?
Yes.
Is this also true?
Why?
Because it's in this coordinate system.
So it's yes, positive.
Okay, for 0 to 90, this is cosine of P is cosine of P is Q, cosine of negative P is also Q.
You just have to know what quadrant.
Huh?
You just have to know what quadrant.
Yes, what coordinate it is. So when you do this particular thing, what is your answer? You don't have a definite answer.
It's just,
It's either P or minus P. So now you have to figure out what is the definite answer. You get it?
Yes.
So you have to figure out, look up. So that's when you have to use tangent inverse. Okay? We'll talk about what I want you to do is go through problem number 4.1. Example 4.1 in textbook. And tell me if you follow example 4.1.
like I said, it's just,
Huh? Okay? Please follow example with this thing. And of course, I also want you to do that extra credit work. Algorithm 4.1.
MATLAB is extra credit or is it extra credit?
MATLAB is extra credit. So this is your next exam will be on this topic. Okay, this one and